Okay, then we wait till exactly 6 o'clock, then we start. Okay, so my clock rings 6 o'clock, so we start. Okay, so again, just to put it very clearly in the screen in front of you, right? Remember, as we said, essentially getting to the Zoom class via our Luminous conferencing. So you all are here, so obviously you all know that this is the way to do it. Then remember, final exam will be in person, face-to-face, okay, in some allocated room in NUS, which will be informed to you all nearer that time. So final exam will be in person, face-to-face. So very important to make sure that you are physically present in Singapore, right? So last week, we already started talking about some of the basic information, right? And then very, very important part, right? Very, very important part. We talked about how the module will be created. Okay, so, well, I wouldn't repeat all of that because as we said, everything that we described last week, that's recorded in the Zoom recording, and I'll mention more about that in a moment. So remember, all right, this is how the module will be assessed. Then, of course, there are the other details on syllabus, which you can read for yourselves. Right, okay, so essentially, again, most important, all right, to remember, final exam will be face-to-face. Okay, then let's go to the announcements. So I've mentioned these things that essentially many of the things will be handled via Luminous, right? Then, as I also mentioned previously, I said, you know, a lot of the things we will do by hand. Okay, we'll do by hand, and you saw how we did that in last week's class. Then after I finish doing by hand, as I promised you, all right, quite soon I will upload the full version with all the handwritings. In case some of you are worried that you miss out something. So the full version is uploaded. Then usually I'm also very quick to upload the Zoom recording. All right, then just to remind everyone, all right, some people have already looked quite carefully at the Zoom recording because we can actually see. Okay, so basically to get the Zoom recording, all right, if you recall, you just go again to conferencing, right? So these, when you go to conferencing, these are the existing and upcoming classes, right? But to go to the Zoom recording, you go on top, you press the previous button, then you see the last week's class and all the previous classes are there. You just click on it. All right, then what happens is that it opens up the link for you to go to the Zoom recording. Of course, you need to note the password. All right, you just copy it. When you open it, it will ask you for the password. You just paste the password in. Okay, so that is very straightforward to do the conferencing, right? Then, okay, so all the classes are down there. And ELAB sessions, as I mentioned, are also down here, right? Okay, let me quickly check. Okay, so Gayatri is here. Gayatri, welcome. I saw your email, so
yes, Prof.
welcome. So you
Thank
see
you, Prof.
the ELAB sessions are also listed here. Okay, specific to what you had mentioned in the email, like Gayatri, in addition to being able to liaise with all the GAs, all right, as you had done, okay, as you had done. And in addition to that, I've actually typically liaised with my GAs and in previous years, right, in previous years, and I'll remind them again, right, that even these ELAB sessions, it'll be recorded over Zoom, all right? So it will also be recorded over Zoom, okay? So while you can attend, and then if let's say something you want to check again, you will play the Zoom record. But for those of you, you know, you have to arrange other sessions. If you want to actually see what happened ahead, then of course you can also use a Zoom record. So even the ELAB sessions will be recorded. Okay, let me go back to the announcements. Right, so as we said, whatever I had done, I would upload it in full. Then I'm also quite quick to upload the Zoom recording. So I've just mentioned how to get to the Zoom recording, right? So you've seen that. And then, as I said, right, these are my GAs. Okay, so indeed, understandably, right? Understandably, some of you, you are actually working. So these hours, which we had mentioned, may be difficult for you. But as I promised you, I said, you just contact my GA, copy me, okay? Feel free to copy me. So that at least, actually, I prefer that you copy me, even though I may not have the time to just acknowledge or whatever. At least I want to be aware, okay? Okay, contact them to make your arrangements. So some of you may need alternative arrangements, so contact them. Okay, as I also said, I said some of you, you know, in addition to alternative arrangements being possible, some of you, after you do session 1, session 2, you might want to do more sessions. That's also possible. So you also contact my GAs, all right, and they are under instruction for me that, okay, they should accommodate the request for extra sessions. Of course, what they will do is they will await, all right, a few of you contacting them, then so that they can kind of collect the few of you together and arrange for time possible for the few of you, which will be much more efficient, right? So I put down here again, as I mentioned, right, the lab session. So you saw that's already been programmed, right? Last week I also showed you those very, very detailed versions, all right, of the briefing notes in addition to the standard ones, which will help you to write the report. Okay, so that. Then remember last week, I had mentioned, all right, in response to some question, what was the deadline? I had mentioned, I said, we are very kind. All right, the deadline is all the way into reading week. All right, reading week is the week just before the exam week. Okay, so you're doing, at least for my part, you're starting to do the CAs during recess week, and we give you a lot of time. All right, so even Prof. CA2, essentially, I think by about week 9 latest, you will already be starting to do Prof. CA2. All right, so we do give you a lot of time to write your reports, all right, all the way up to reading week. But as I said, you know, on the one hand, we are kind. On the other hand, it also means that our expectation is that, you know, you do your work. We want you to, you know, don't just hastily do it. After you do it, we want you to think about it, all right? And then work on it, improve it further, all right? Then, of course, you know, those people who really spend a lot of time, it's very clear one now, the persons who put in the real effort and the persons who do very, very quick job, very, very clear one now. Okay, so it'll be there. And where you will make the submission is, you go and look at our files, all right? That has not been opened yet. 5104 people will submit to the 5104 submission folder. Okay, if you you cannot see it because it's closed, but I can click on it. So you will see that, okay, 5104, you go in there, there's a CA1 report, CA2 report, CA3 report. Okay, so that's 5104. Similarly, 6104, all right, you will also see you have a CA1, CA2, CA3. Okay, and nearer that time, at the moment, even though you cannot go into it, we haven't kind of restricted the visibility yet. So even though you cannot click on it at the moment, you can see both. But nearer the time, what will happen is that in order to prevent and make sure that there are no mistakes, to prevent any mistakes, what will happen is that 5104 people will only be able to see your 5104 folder. Okay? Nearer the time, we will change the settings. 5104 people, you will only see your 5104 folder. 6104 people, you only see your 6104 folder. So no danger of mistakes. Okay, then also in a way, it also puts your mind to rest, because as we told you, I said, don't worry, that there are 5104 people, then there are 6104 people, who was essentially supposed to do more advanced material. Don't worry that they are competing with you all. No. Okay, the grading is totally separate. 5104 people is 5104 grading, 6104 people is 6104 grading. Okay, so with that, then again, then those are the key important matters that we had mentioned last week. Okay, with this, let me pause. All right, let me pause for a while. Check. Anyone has any questions at all? You can either put it into the chat or you can speak into your microphone to ask whatever questions that you want to ask at this point, just on this basically direct, straightforward admin and arrangement matters. Okay, okay. Then if everything okay, then what I'll do is, as I've mentioned to you all, typically, all right, I spend a lot of time doing review and revision just to make sure everybody will be on track. So very quickly then, to do the review revision, remember we said, okay, with adaptive control, we started out last week, even though it was essentially posing a simple example, yet you see the concepts there are very important concepts. Some of the concepts, if you dig further, actually even has the potential to be quite deep. Okay, so anyway, what we did was we said, okay, so adaptive control. Adaptive control, we said, okay, let's start in a very simple way. We said, let's look at some system we want to control, right? Typically called the plant. Our system that we want to control, and we start with a very simple system, a first order linear system, yp dot equals to apyp plus kpu, right? And then we said, look, typically in controlling these things, right, you would want to put some kind of specification, and you would say, look, after I finish controlling this thing, I really want it to be the kind of situation that, when I finish controlling this thing, all right, I would expect some kind of performance to come out of it. Okay, let's say, for example, if I put in a step, all right, I would expect this kind of a response at steady state, is exactly the same as the step that I put in, and then, it rises with some particular speed of response. So clearly you see down here, the moment you say you want this kind of response, you've already said what you want out of your control. You said you want, basically steady state to be exactly the same, matching your command input, and then you say you want a certain speed of the response, all right? So if that's the case, if you say you want a certain speed of the response, basically in your reference system, all right, down there, you've already specified a so-called reference model, all right? Speed of response specified by your AM, all right, a stable system, and whatever number you choose for the AM will specify your speed of response. Then with the associated KM, you would have specified that, look, you want the steady state response to be such that they look the same for your command input and your system output. Okay, then we said, okay, with this, what is very, very clear in such a simple system is, okay, to be able to get this kind of thing, this kind of system, you give me this kind of system, I know I'll feedback the output, I will do a scaling gain. So typically then, all right, we already know that something that would work would be a control signal like y equals to u equals to theta yp plus k times r. All right, and then we say, okay, let's see, substitute this in and see what happens. We substitute this in, And then, you can see based on simple rearrangement, you can see, look, if you substitute in this way, right, and it becomes like this. And somehow, if you can find a theta to make this thing exactly AM, and you can find a K to make this thing exactly KM, so these are then your perfect control gains, right? Theta star and K star. Then if you have this exactly like that, then what happens is that in your control arrangement, in that simple diagram down there, you've been able to get the closed loop control system to be YP dot equals to AM YP plus KMR. All right, and then it's quite easy to check. If you now look at the tracking error, which is the difference between YP and YM, all right, you just check, all right, because E1 is equal to YP minus YM, E1 dot will be YP dot minus YM dot, all right, YP dot minus YM dot, and now with the proper arrangement, with the proper perfect control gains, YP dot is now AM YP plus KM. YM dot to begin with was AM YM plus KMR. So, you make a simplification, it turns out to be E1 dot equals to AM E1. And then with how you specified your reference system for your desired closed loop is a stable system. So AM is less than 0. Clearly, you see the tracking error dying away. But of course, this would be, as I said, for the situation whereby is the normal situation. We're not doing adaptive control yet. This is normal situation. And this is what you would do. All right. And this would be exactly what happens if you know how to exactly put in the perfect control gains. Right? You put in the perfect control gains. Okay, this is where we can start talking about adaptive control. All right, because now we will say, look, we want to get exactly the same thing, but we want to do it under a situation whereby we don't know AP and KP. If you don't know AP and KP, you cannot calculate theta star and K star, right? So, okay, but we still want to do the same thing. So the first thing that we know is we said, look, we already know this control law work, all right? This control law, we know that it would work. U equals to theta times Y, K times R. We know it would work. Just that we don't know how to calculate exactly theta star and K star. So we said, okay, to start one way of doing adaptation, right? We said, okay, I know this structure works, but I don't know how to, what gains to put in. So why don't I make these gains changing with time? All right, and if I make them changing with time, if I can find some way to update or adapt them such that I still get the same kind of, performance that I got even when the system is completely known, and that would be wonderful, right? And this is where, we can even start talking about adaptive control. Okay, so we know the control law works, but we don't know what control gains to put in, so we use the same control structure, all right, with the control gains, but we made this time varying. And now we have to decide how to adapt it. Then remember, as I said, okay. Essentially, it comes from a design rule, all right, which by the end of what we do today will also become quite clear to you all. Okay. But up to what we did last week, what I simply said was, all right, since I need to find a way to adapt it. Last week, I just simply told you, okay, I'm going to adapt it in this particular way. I'm going to adapt it in this particular way. All right, for the theta gain, I'm going to adapt it as I take the tracking error, because tracking error, all right, YP you can measure, YM is from your reference signal. So E1, the tracking error you have, the YP signal you have. So I take YP times E1. Then I put in any gain, gamma 1. The only condition on gamma is that it needs to be a positive gain. So just any positive gain. All right, then in this way of doing it, I need the information on signum of KP, sign of KP. But as I said, this is quite simple to get. You basically take the system, give it some kind of input to push it and see which direction it moves. Okay, so this would be the easiest way. But as I also said, if you go into deeper research into adaptive control, I can even remove this knowledge for you. But of course, that goes on much deeper lah. Okay, but now mind this simple version first. We look at this simple version. So tracking error, YP, gamma, any positive gain minus signum KP, and this is how I would adapt my theta. And you can see this is basically, you know, you can exactly even set this up, all right, if you are doing simulation, all right, with Simulink, for example. Okay, you can set this up as a graphical thing. Basically, what you do is you take the signal E1 multiplied by the signal YP, all right, then you multiply by a positive gain, then whatever your sign is, you put it down there. And then basically you take this whole signal, pass this through an integrator, and that becomes theta. All right, so basically this can be set up. So this is something which can be completely set up because all the signals on the right-hand side are known. You pass it through the integrator, all right, this implements this particular update law. Similarly, all right, implements this particular update law. All right, here you take the output error, you take your reference command signal, and that you have, all right, because this is what you say should be the command signal. And again, gamma 2 is any positive number minus signal KP, and you generate the update for K. Okay, in particular here, because you've seen the result from last week already when we finish everything, in particular here, all right, even though I didn't say it last week, I can say it now at this point. This is all that I need. Okay, this is all that I need. Okay, gamma 1, gamma 2 only needs to be positive gains. All right, they can be anything. So as I said, you know, last week some of you said, you know, essentially some of the learning laws are like that, and it's true. It's true. Some of the learning laws are like that. All right, except that the learning laws, because the way they are done is a lot of it is by approximation. It is not as powerful as this. All right, you will see a lot of the learning laws say, okay, you want to put some gain, but you better try some small gain, because if you put too large gain, the thing may not work, or the thing may bomb out. Here, I have no such restriction here. I have no such restriction here. Okay, my only requirement is gamma 1 and gamma 2 are positive gains. All right, and then these are the signals I use. The other thing that you would also have noticed, even though I didn't say it last week, because, you know, before we finish everything, you know, it makes no sense to say it. So as I say, this is everything. Right at this point, the other thing that, you know, you can see is that, look, I have no constraints and no restrictions on how I start this thing. All right, there's no need for me to say, look, you better start, you know, okay, you are basically guessing some control gain here. You better start near. If you start too far, it may be dangerous or whatever. Again, you see no such requirement. All right, I just use this control law. All right, I use this update law, and I can start anywhere I want. All right, I can start. All right, I can start to begin with. All right, I can start theta. If I have no knowledge, I can start theta at 0. All right, and that will work. All right, if I have some knowledge, I can start theta close to theta star. That will work too. All right, if I'm crazy and I say, look, I want to start theta very large. I want to start theta, the gain at 10 million. That will also work. Because you see, in what we have done, there are no restrictions on where you start theta and where you start K. All right, and there's no restrictions on anything. This is the entirety of it. All right. So the approach is carefully done. All right, it's very powerful. There's no guessing, no approximation. All right, because you saw a final result. All right, so remember what we did? We said, okay. All right. So now, since this is how we're going to adapt it, and since now it is not the normal way in which control in undergraduate is done, and even control in 5101 is done, there's no such thing as you know, stable poles or whatever. All right. So how are we going to say whether this works or not? Okay. So we said, okay. Here, because you no longer can hold on to linear time invariant concepts. All right. So one reasonable way to start would be to say, okay, look at the signals that we will be interested in. All right. Certainly, E1, the tracking error, will be something of interest to us. All right, because basically we want E1 to go to 0, right? So E1 is of interest to us. We are also interested in the error between the control gain that we put in and are adapting. So remember, we are adapting this, right? We are adapting this. So it's changing all the time. But we also know there's some perfect gain, even though we don't know what is its value. Okay, we don't know theta star's value, but we know this exists. All right, because in the way that we set up the problem, we know this in this particular problem, this number exists, even though we don't know it. All right, we don't know this number, but this number exists. Okay, theta is something we generate. This theta star exists. So clearly we are interested in the difference between theta and what it perfectly should be. Similarly, we are interested in K and what it perfectly should be, right? So certainly I'm interested in an error signal, all right, parameter error of theta. So this is a parameter error, the error between theta of t and the exact theta star. So I'm interested in the parameter error phi. I'm also interested in the parameter error c. So these are the signals we're interested in, okay? So if you're interested in these signals, okay, so we said, okay, how about let's now carefully see how we might look at them carefully. So I said, okay. Since we are interested in these signals, typical simple way would be to say, look, we're interested in E1, phi, C. All right, so typically we would be interested in some kind of three-dimensional surface created by these three signals, and a very easy three-dimensional surface would be E1 squared plus phi squared plus C squared, right? E1 squared plus phi squared plus C squared, which, you know, without all those numbers, that would be a spheroid, all right, in three space, right? And it extends to n dimension, all right? If you have, it can be 6 space, 7 space, you know, n can be anything. All right, but here this is just simple 3 space, right? So it would be the spheroid, except that, okay, because in the system, there are various numbers in there. If you purely look at a spheroid, it will not work. All right, so we have to kind of moderate it with some numbers. So here with the phi squared, I moderate it with magnitude of Kp divided by gamma 1. Okay, here remember, I'm just looking at these things conceptually. All right, conceptually, so basically magnitude of Kp exists even though I don't know the number. All right, because I don't know Kp, so I don't know the number magnitude of Kp. But still magnitude of Kp exists. Gamma 1 is chosen by me, a positive number. Magnitude of Kp, gamma 2 is chosen by me, also a positive number. Okay, so basically this is conceptual. This ellipsoid is conceptual. Then I say, okay, I look at this ellipsoid, and once I have this ellipsoid, all right, what I would be interested in would be to see how this ellipsoid is changing with time. When I say that, obviously what this means is that I'm interested in the DDT of the ellipsoid. So ellipsoid being what it is, right? Being what it is, if I take DDT, all right, it simply turns out to be 1/2 of E1 squared after you DDT will be just half, and the 2, there'll be a 2, half and the 2 cancels, then there's E, then you have to take E1 dot, so E1 dot. Similarly, those would be magnitude of Kp over gamma 1 phi dot, magnitude of Kp over gamma 2 C dot, right? So it just turns out a bit like this. Then remember what we did, we said, okay, now we need to look at this term by term, because E1 dot, we already knew something about it. All right, E1 was Yp minus Ym. So E1 dot would be APYP plus Kp. Yp dot would be APYP plus Kp times U. All right, then we substitute for U in there. U was theta Yp plus K times R. And even the K, the theta I separated out. Theta I separated as phi plus theta star. All right, that's based on my definition of the parameter error. And the K I also separate out as C plus K star. All right, and then I say, hey. But on the other hand, you know, AP plus KP plus theta star, all right, is exactly AM, and KP K star is exactly KM. So if you now simplify this thing and work this out, all right, as I told you, you go and double check for yourself. This time now should just simplify to A1 AM E1 plus KP phi YP plus C times R. And that's an important first part of the expression for us coming out of this work that we do, all right, is first part. Then I said not further, because in the DDT of V, we also have phi dot and C dot that we're interested in. So if you look at phi dot and C dot, phi is theta minus theta star. So phi dot is just this whole thing differentiated with respect to time, but theta star is just a number, a perfect number. So theta star dot is just 0. So phi dot is exactly theta dot. All right. So you can see now phi dot is exactly theta dot, and theta dot was what we designed it. This was our design. Minus signum Kp gamma 1 E1P YP. All right. So you can see now how our design is coming in. Similarly, C dot by the same token is minus signum Kp gamma 2 E1 times R. All right. So all these three expressions are very, very important. All right. Very important. So we make use of that. We go in there and look at our V dot expression, right? Remember V dot was, right? V dot was E1 dot, magnitude Kp gamma 1 phi dot, magnitude Kp over gamma 2 C dot. We've got E1 dot, now we've got phi dot and C dot. So what we do now is we write everything down. E1 dot is this, right? E1 dot is this. Then magnitude Kp gamma 1 phi dot was this inside the curly bracket, right? And then this is magnitude Kp over gamma 2 C dot. C dot was exactly this as well. Then we say, okay. This is how we have made use of our design flexibility. Because remember, this part was designed by us. And you can see now why we design it in this way. We design it in this way, all right, especially because now we know okay, this will come out in this particular way. So this part was designed by us. Then you look carefully at how it contributes. All right. The magnitude of a number, the sign of the number give you the number itself. All right, but it's a minus sign. Okay. So basically this gives us minus Kp, gamma 1 cancels. So you have phi Yp E1. And you look at this. This is exactly Kp phi Yp E1. So these two terms exactly cancel. And similarly, because we have designed in this way, these two terms also cancel, leaving us with V dot equals to AM E1 squared. All right. And that's nice because remember, by design, AM for the reference model being a stable reference model, AM is less than 0. So that says that now V dot now, as a result of our design, all right, V dot is always a quantity which is less than or equals to 0. All right, so remember what we've done? We started off looking at this ellipsoid in 3 space. All right, involving the signals E1, phi, C. Right? Clearly, we're interested in how it changes with time. And here we've just finished finding out that the way it changes with time is that this ellipsoid V dot is always less than or equals to 0. What does that tell us? That tells us that, look, whatever ellipsoid that you started out with. So remember, as I said last week, I said, we started the adaptive controller at the beginning of last week's class. All right, so at the beginning of last week's class, okay, there was a particular value when we started at time 0, all right, T0, particular value for Yp, Ym, all right, particular value for whatever you put as your initial theta, initial Kp, all right. And those are initial values, and whether they are large or small, it doesn't matter. Those are initial values. Even if they are large, they are still a number. Okay, so you calculate the number and you build your initial ellipsoid at time 0. All right, at the beginning thing. And this initial ellipsoid, what we've just shown is that, all right, with this initial ellipsoid that you started out with, this initial ellipsoid can never increase in size. All right, so no matter what your signals are, no matter how large, it is still a finite ellipsoid. And the ellipsoid cannot grow in size. So what that says, all right, first of all, straight away is that we have this very, very nice property that if you have an ellipsoid like this, and you show that V dot less than or equals to 0, all right, the first thing that you've shown me is that, look, all right, the signals that you are interested in comprising that ellipsoid, which is E1, phi, C, these signals therefore now are bounded for all time. And remember last week I reminded you why this is very important, because we are no longer talking about linear time invariant systems. All right, now there's non-linearity in the system. Because as I said, you look carefully. All right, look carefully at your adaptive law. Straight away in your adaptive law, E1 is Yp minus Ym. So in the theta dot part, there's Yp squared already. Yp squared, because E1 is Yp minus Ym, there's Yp squared minus Yp times Ym. So there's already non-linearity in your adaptation dynamics. So you no longer can hang on to linear time invariant type of concepts to say that you are guaranteed existence of solution, because there's no such thing of guaranteed existence of solutions anymore. So here I have to prove that solutions exist and they are there, for all this time that we're looking at it. So I've just finished showing you that, because you started off with a finite ellipsoid. I'm just showing you that, in this way of adaptation, no matter what happens, all these signals will stay bounded for all time because the ellipsoid cannot grow. So they'll be bounded, okay? Okay, they'll be bounded because it's an ellipsoid, okay? These things, they can interchange in their magnitude. Some can become larger while the other can become smaller at the same time. But never mind, even if they become larger or smaller, they still cannot, okay, become unbounded because they are all bounded. All right, and remember I told you last week why this is important, because in nonlinear system, I can construct for you a very simple first order nonlinear system. All right, and I can construct for you and such that if you want it to disappear in 0.1 second to disappear to infinity, I can construct for you that system. All right. You want it to go even faster to infinity, you say you want it in 0.001 second, I change it and the system can disappear to infinity in 0.001 second. All right. So in nonlinear systems, okay, there's such a thing as finite escape to infinity. So you have to make sure, even before you talk about any other properties, nice or whatever, you have to first of all show me that the solution even exists for the time that you're talking about. So I've finished showing you that. All right, then the next thing is, okay, we said, okay. We've just shown that V dot is equals to this. Then I said, okay, in order to avoid ourselves confusing ourselves, all right, I said, why don't we change this AM to minus alpha, making alpha a positive number, so easier for us to see. All right, so we write it that way. This is just minus alpha, then write it, and then integrate both sides. All right, I integrate from the beginning of last week's lecture time, the beginning time, all right, to any time, because this expression is valid. So I integrate to any time, all right, even including up to now is valid any time, all right, starting from whatever point you started out to any time. All right, this expression is valid. Okay, then if I check out how this integration works, this one, when you integrate, it just becomes V at whatever time minus V at your initial time. All right, this other part of it, I just let it remain, noting that alpha is a positive number. All right, then I bring the this part over. Okay, if I bring this part over, all right, I rearrange it, make it easier to see. Okay, so this is alpha is a positive number. And basically, I have this result that if I take the tracking error signal squared and integrate it from the beginning time when I started the adaptation to any time at all, all right, is the property of the system I've just set up is such that the tracking error squared, all right, as an integral always obeys this particular relationship. Okay, V at time 0, as I said, was just the value of the ellipsoid that we started with, and it will be finite. It can be large, all right, but no matter what, whether large or whatever value, is still finite. It's still finite. Okay, so it's some finite value, and this is always a positive value because of the way V is defined, right? See, V is defined in this way, right? The ellipsoid is defined in this way. Okay, so VT is always a positive term. This is always a finite number. It may be a large number, never mind. Okay, but whether large or whatever is still a number. It's just a number. Okay, a number that cannot change. All right, it's actually just a number. Okay, so this function in time V of t is an ellipsoid as a function of time is always positive. So if you remove it, so it's bounded from above by this number. We rearrange it. Alpha is just a positive number. Rearrange it. Then just another number, and I write it out clearly as a number C1. Okay, then I say, look. Stare at this signal carefully. Okay, it's saying that with the way that we are doing our adaptation, all right, it is such that, all right, as you go and track the tracking error, all right, the tracking error squared when you take this integral for whatever time, starting from the beginning, it's always bounded from above by C1. All right, what kind of a signal is that? All right, okay. Some of you say you know signals and systems very well. Fine. But as I said, if you honestly study deeper into signals and systems, this would be what is called a class of square integrable signals. All right, it's obvious. What it says is that you look at this signal, when you take a square, it's always integrable. All right, because no matter how long you take the integral, all right, it is bounded above by a fixed number. This is called the class of square integrable signals. All right, also called labeled by, all right, for those of you interested, if you go and look at real analysis, all right, the class of capital L2 signals from 0 to infinity. Okay, never mind. We just know this, it obeys this property. That's the first thing. All right, so as I said, if it's the class of square integrable signals, and remember, as I said, you want to take the integral because we are studying signals very, very carefully. All right, we're studying signals very, very carefully. We cannot be slipshod. If you look at an integral now, you got to define the integral properly, rigorously. And if you look at the proper definition of integral, it is basically looking at measure theory. Okay, so you have to look at integration via measure theory. All right, so we look at that, but never mind. Okay, so as I said, what kind of signals is this class of square integrable signals? What does it look like? All right, so I said, okay, let's try to see at what signals might be. I say, for example, look at the orange signal. All right, so you look at the orange signal, clearly it cannot be the orange signal because the orange signal, every time you integrate the E1 squared, it will accumulate value. And if it all the time is like that, when it accumulates value, at some point it will violate this constraint. So clearly the class of square integrable signals cannot be of the orange type. Okay, that's the first thing. Next thing is we look carefully. Okay, maybe, okay, then the blue type. In the beginning, it's large. During the transient phase, it accumulates integral. But at some point, where it's already, reaching C1, clearly this class of signals cannot accumulate integral anymore. So it begins to die away, and it looks like that. So the blue class of signals clearly would be what a class of square integrable signals would look like. All right, except that if you look at this thing carefully from the viewpoint of measure theory, all right, signals from the viewpoint of measure theory, signals and systems by measure theory say, okay, square integrable signals can also be of the type where it's the blue with the spikes in the red. All right, these are spikes, where at the point, the measure underpinning it, that's why it's called measure theory, the measure underpinning it is 0. Okay, it's just a spike. Measure underpinning it is 0 and just a spike. Underpinning is 0, just a spike. And you can see, okay, basically this part will be the measure. If the measure is 0, even though whatever spike it is, the measure times 0 is still 0. So there's the danger that square integrable signals can be the blue type plus, you're right, spikes like that standing on support set of measure 0. Okay, as I mentioned to some of you last week class, these are not impulse, because impulse will be even worse, because when you integrate over an impulse, it accumulates integral. So impulse is definitely not admissible. But even if impulse is not admissible, these spikes standing on support set of measure 0 are admissible, and that becomes a problem. All right, because when you look at signals and systems, and you look at signals rigorously, you have to be very careful. It can be like that. But fortunately for us, it's not like that, because in our case, we can look further. We can look at E1 dot, all right? And we know E1 dot was AM E1 plus KP Phi YP plus KP CR, all right? And from our earlier establishment, we've just shown you that in our whole system, these signals are bounded for all time. E1 is bounded, Phi is bounded, C is bounded. All right. So if E1, Phi, and C are bounded, we now carefully check E1 dot. All right. E1 dot is AM, E1. AM is just a number. E1 is bounded. So this part is always bounded. KP is a number. phi is bounded. We've just finished showing that. Yp, okay, can be shown to be bounded because Yp from E1 equals to Yp minus Ym. Ypm is your reference signal. Your reference signal, the way you generate your signals and what the signals you want to use, Ym has to be bounded. E1 is bounded. E1 is Yp minus Ym. E1 is bounded. Ym is bounded. So Yp is also bounded. So Am bounded, E1 bounded, first signal is bounded. Kp number, phi is bounded, Yp bounded, this is bounded. Kp is a number, C is bounded, Rp is just your reference command signal, which is bounded, so this is bounded. So if you do a check on E1 dot in our system, E1 dot is a bounded signal for all time. All right, so for those of you again interested in signals and systems, interested in real analysis, all right, E1 dot being bounded for all time, E1 dot belongs to the class of L infinity signals from 0 to infinity. All right, and here I've carefully showed it by way of showing you this thing, showing you this diagram, okay? But there's a result in signals and systems that say, okay, if you give me an L2 signal, all right, and you also tell me that its derivative belong to L infinity, an L2 signal with derivative belonging to L infinity, there is a result called Babolat's lemma that shows that the same thing that said, okay, with those two things, all right, limit as E1 tends, as T tends to infinity, it has to be the only type of signals, all right, where with E1 belonging to L2 and E1 dot belonging to L infinity, all right, square integrable plus E1 dot bounded. The only type of signals that can satisfy this will be the blue signal, no red spikes, all right, leading us to the conclusion that we needed. Then in the way that we are doing adaptation, we have gotten what we want, limit as T tends to infinity of E1 equals to 0. Okay, with that, let me very quickly switch to the typewritten lecture notes. It's basically the same thing. Okay, you set up the system. There I've written it in differential operator form, but basically it's the same thing, right? Exactly the same thing as I said. Then you put the adaptive controller, okay, and then you have this time varying controller gains, all right, and then well, as I said, you can actually write it like that. All right, it's the same thing, okay, and then basically with the reference system, you go, well, we did it by hand last week, so that's why I'm going through, just flashing it through. All right, this is exactly what we said. All right, with all these things, okay, then the result is that, okay, E dot is bounded, E belongs to square integrable, okay, that's the result, all right, also known in signals and system as Babolat's lemma, but I wanted to show you exactly what it looks like pictorially, so that guarantees for us this. So what we've done last week basically can be summarized down here, right? Summarized down here. I look at a simple system, I set up this reference model. I know this control law works, all right, but I don't know the exact gains, I put in time varying gains, okay? My adaptive law is like this. Okay, here I said I put it to be 0, but actually you don't need, there was no requirement. So instead, you also see I said can be arbitrary. Okay, can be arbitrary. It doesn't need to be 0. Okay, if you want to put 10 million, also fine, as long as it's some finite number. Okay, so you can set it with anything. All right, and with this way that we've set it up, which is what we did last week, the result that we have, all right, the result that we have is that if this adaptive controller is applied to this system, we are guaranteed that we got the tracking error equals to 0. Okay, so this is summarized now very simply what we've done last week. All right, as I said, you know, this is quite straightforward, yet there are some deep ideas in there. And as I said, you know, many of you are already familiar with MATLAB, Simulink. If you're not familiar, you better start familiarizing yourself now, because all the CAs need that. Okay, so as I said, you know, this simple system, okay, you can actually set it up, put in some numbers for this. All right, choose a suitable reference model, set this up, and you can already see the performance of the system. Okay, so that part is quite interesting. But more than that, I again want to emphasize for you that look here, this is exactly that. In fact, this line, I shouldn't have put this line. because this is not necessary. As I said, it can start anywhere. It can start anywhere, all right? And then what happens is that I'm guaranteed, and there are no constraints on what gamma 1, gamma 2 should be. They only need to be positive, all right? You can start with the YP anywhere, the YM anywhere. You can start with any initial gains, and my result is guaranteed. My result is guaranteed, all right? Okay, with that, let me push on a bit further before we call a break. We will call a break. Okay, we will call a break. So, never mind, let's skip this thing. All right, even though we didn't say it, all right, what we have done in detail just now. All right, what we've done in detail just now actually follows along the lines of what is called the Lyapunov direct method. All right, building upon a state variable description. All right, okay, I have my students here. Yanhan and Jiewen studied state variables with me last semester, right? Afterwards, I'll say something about this, which will be familiar to two of you, Yanhan and Jiewen, which is basically exactly what we did in 4302 last semester, state variables, okay? So basically, whatever it is, you are looking at a suitable system in state variables. And then, all right, what we've done is equivalent to this, where basically we have now looked at the so-called ellipsoid function, all right? But the generalized version says that, look, even though I call it ellipsoid, it says, look, whatever function you have better satisfy this kind of a property called positive definiteness. All right, and you have to be very careful, Positive definiteness is a very, very specific definition given like this. It's not a positive function. Okay, you find any positive function, and you don't satisfy this kind of property, then what you're doing is not correct. Okay, so afterwards I'll say a bit more about positive definiteness. All right, and I'll show you that what we have done actually satisfies this. So it says, look, you're going to look at some kind of a function. All right, here we chose the ellipsoid. Okay, and then there's also the other property of also called decrescence. This is bounding from below, all right, of a K-class function. All right, this is bounding from above. Then if somehow by design, you can show me that your V dot turns out to be semi-negative, semi-definite. And in addition, if you have the property that whatever you are putting together as your so-called positive definite function, if your positive definite function is such that it also has the property of radial unboundedness, right? Then what it says is that, all right, if you have all of these properties, actually we are only interested in the full set of the properties, then it says you have a very powerful result. That really your adaptive control is such that, when you build it in that way, you're not going to be restricted by anything. All right, so we'll look at that carefully. Okay, and we will also go on. Okay, with this, of course, based on Lyapunov theory, some other results will come about. And this one you should be familiar from linear systems, right? Basically, this is a linear state variable system. Okay, if let's say you say A is a stability matrix, then clearly this is a linear system. A have a negative real parts. But more than that, and we will use this, all right, that if it's a stable linear system and A is a stability matrix, then this relation also holds true. And we will use it shortly. All right, so stability theory is very, very wide, okay? Our module is not about stability theory, it's about adaptive systems. We will just use stability theory. Okay, so after the break, I will very, very quickly, after the break, we will have a break shortly. I will very quickly show you, indeed, even though we didn't say we were using the ideas from the Lyapunov direct method, yet, in what we have done last week, all right, what we have done last week, we didn't try to pull up some big names. We did it by first principles carefully, all right, and then you see essentially, all right, this is the same type of idea in a more general context, all right? So as I said, stability theory has this kind of related results coming from it, which we'll use. And with that, then after the break also, since we have done the first order case, next thing we'll do is we will go on to adaptive control, where, okay, in a situation whereby we can measure all the state variables. All right, so that's what we will go on to. But at this point now, before we try to do too much more, okay, let's take a break. So let me stop the recording. Okay, so remember, as I said, what we did last week, we did it very, very carefully, right? And we didn't try to hide behind some big results, some big names, right? We systematically showed it so that it's very clear exactly what's happening, right? And just now, I then went on to say, well, if you look at all these things now, all right, really actually, the approach, the so-called approach called Lyapunov's direct method, is essentially along this line. All right, what Lyapunov's direct method says is that, I mean, Lyapunov's direct method is not about adaptive systems per se, but what it does say is that it says, look, you go and tell me what system you have. You write it out in this state variable form, right? You write it out in this state variable form, right? Even for my 4302 class, my students know, okay, basic state variable form is, all right, on the right-hand side, you know, you have all these signals that you call state variables, and they will all be on the right-hand side, and they can have all kinds of things, but those signals, which you call state variables, must appear on the right-hand side with no derivatives. Then the same signals which you claim are your state variables must appear again on the left-hand side and appear only as first derivative. So essentially, you must be able to put it in this particular way. All right? Okay. So Lyapunov's direct method says, look, if you have a system in state variable form, then, all right, if you want to understand some aspects of how this system is behaving, or what you've designed, how it works, all right, then one way would be to now look at a so-called scalar function. All right, and this scalar function, all right, first of all, it must have the properties of positive definiteness. All right, positive definiteness is very exact. It's not just a positive function, it's a positive definite function. What that says is that, look, you know, you are finding a positive definite function of your set of state variable x. All right, of your set of state variable x. All right, if you say it's positive definite, then you must be able to find for me a continuous non-decreasing scalar function alpha, such that alpha 0 equals to 0, and your so-called function that you create must be bounded from below by this same alpha function, taking as its input to the alpha function, all right, its argument norm of x, all right? Whatever you say this x down here, you put norm of x down here, alpha of this norm of x, you must find this alpha function, which is continuous non-decreasing scalar function. And your v of x of t must be bounded from below by alpha for all t. Okay, only then would it be considered positive definite, right? And then there's this associated property of decrescence, which says, okay, on the other hand, if you can find also a beta function, which is like the alpha function, exactly like the alpha function, right? Beta, its argument is also norm of x. But now this beta also continuous non-decreasing scalar function, and it bounds v from above. Okay, so it says positive definite decrescence. If by your design, all right, you're able to show me v naught is negative semi-definite, and in addition, if your alpha function has the property that, you know, as norm of x tends to infinity, your alpha function also tends to infinity. That's called the property of radial unboundedness. Then you have all the properties 1, 2, 3, and 4. Then it says that your system has the property of uniform stability in the large, which basically is what is sometimes loosely called as global stability. All right, so okay, so now let's go and see carefully. All right, again, what we have done. Okay, okay. So remember as we said, now we're going to tie what we had done last week, all right, to this so-called the upper of direct method. So basically, the upper of direct method says, look, you know, you have this state variable system, you check for positive definite decrescence, then you check that your V dot is less than or equals to 0, and your V if it's radially unbounded. Okay. So let's go back and look at, let's go back and look at our system. What do we have? All right, you go back and look at it very, very carefully. All right, you go back and look at it very, very carefully, if I can find it very quickly. Okay. So some of the things quite important. All right, we remember we had this set of dynamic equations coming up, right? Then we also looked at E1 dot. All right, we had this. So now let's carefully write all of this down. All right, remember what we had? We had E1 dot. All right, E1 dot. Okay, let's write it down. Let's write it down. Okay, let me now write it down carefully. Right, so if you go and double check what we had, E1 dot was AM E1 plus, all right, you go and double check, phi of t, yp of t, all right, plus phi of t, sorry, phi of t, c of t, all right, times r of t. Right, that was one expression that we had, okay? Then the second expression that we had was phi dot, which was exactly theta dot, which is what we use as a design equation, equals to minus signum kp, all right, gamma 1 e, whoops, sorry. Gamma 1 E1 of t and yp of t, right? And then c dot was minus signum kp gamma 2 E2, sorry, E1 of t r of t. Okay, now stare at that. All right, stare at that, and now you will see that, hey, all right, even though we didn't say it that way, all right, even though we didn't say it that way last week, but this is exactly the set of equations in state variable form, all right? And the signals of importance to us are clearly, right? Clearly E1 phi c, right? Appearing on the left-hand side in first derivative, appearing again on the right-hand side, no derivatives with all kinds of other things. And this is exactly our state variable system now, okay? So as I said, you know, remember this was basically coming from theta of t, a so-called control gain which was being adapted. And this was coming from k of t, another control gain which is being adapted. Now, all these things, so-called control gains and all that, they're just names, you know. Basically, the most important thing is that you have to now rearrange all these things. Huh? Because remember, this is actually a control gain, and you can call it a control gain, but never mind. You know, after you've rearranged this, you will see that really, in what we have done, yes, last week, all right, even though we call these control gains or whatever, these were now the actual signals of importance to us. And these are the state variables of a specific system for which we are interested coming out of our so-called adaptive system. All right, because it's exactly in this form. All right, your state variables, which are E1 phi C, appearing on the left-hand side in first derivative only, then appearing again on the right-hand side, no derivatives with all kinds of other things. All right, so the necessary function from Lyapunov that requires us to put down the effective state variable system is down there. Of course, we start off with some initial condition, right? And the initial conditions are initial conditions in your tracking error, can be anything. Your starting control gain can be anything, right? So, okay, this is essentially already our equivalent set of state variables. Okay, that's the first thing. All right, then as I said last week too, I said the ellipsoid function that we were interested in, basically the ellipsoid function that we were interested in, all right, we wrote it in a simple way lah. We wrote it in a simple way because what we simply did was we simply wrote it really as an ellipsoid, right? 1/2, right, of E1 squared plus magnitude of Kp over gamma 1 V squared plus magnitude of Kp over gamma 2 C squared, right? And that was how we wrote it last week. All right, and it's correct. But as I said, you can also take this whole thing and actually very, very easily rewrite it in quadratic form. If you rewrite this in quadratic form, then 1/2 of E1 squared, you just put a 1 down here. And then this one, you just put in the main diagonal magnitude of Kp over gamma 1. And then you put in the main diagonal magnitude of Kp over gamma 2, right? Then all the other elements are 0, right? I put that in that quadratic form, all right? The reason I put that in that quadratic form, the moment I put that in that quadratic form, okay, some of the next things that I can do for you is I can really show that it will be positive definite, okay? To show that it's positive definite based on what the Lyapunov direct method requires, I have to show you what is my alpha underbounding function. All right, and to choose my alpha underbounding function is very easy. Once I've written it in that quadratic form, or even in my spheroid function, I just, basically, okay, because now clearly, all right, these are my state variables I'm interested in, E1 phi C, okay? So clearly, all right, from the viewpoint of the Lyapunov theory, I need to find the alpha underbounding function, all right, which now says that, okay, my alpha underbounding function can be this one. I take the minimum of all those numbers there, whatever those numbers in the diagonal magnitude of Kp over gamma 1, all right, magnitude of Kp over gamma 2. If I take the minimum of all those numbers down there and multiply by my norm of x squared times 1/2, right? You can clearly see that, okay, if I do it like this, okay, whatever is the minimum, okay, I take it and multiply by this because this is norm of x squared already. All right, norm of x squared already, then 1/2, all right? And if I take the minimum, clearly whatever I have down here, all right, will be bounded from below by alpha, okay? And you already can see what I'm going to do for beta already, okay, to get my decrescence. Because for beta, instead of the minimum, what I do is I just take the, basically the maximum, all right, of those same diagonal terms, the maximum, all right, norm of x squared times 1/2, right? I do that, okay? And then clearly you see that I also have decrescence because my beta overbounds my V function from above, right? Then you already saw last week, I'm not going to do it again, that from my control and adaptive law, I got V dot equals to AM E1 squared, all right, which clearly is satisfy what I need, less than or equals to 0, all right, because remember AM for the stable reference model has to be chosen less than 0. All right, so I already have that. And then finally, the part on radial unboundedness, you go and double check my choice of the alpha function. You check my choice of the alpha function where my choice of the alpha function, remember alpha has to be a function of norm of x, all right? And you saw that I had chosen it to be the minimum of all those diagonal terms times norm of x squared times 1/2. All right. And clearly you can see that, you know, my choice of the alpha function is such that if norm of x tends to infinity, all right, then clearly I do have that radial unboundedness function, because this particular alpha function that I've chosen, all right, indeed tends to infinity. So I do have radial unboundedness as well. All right, so that's why, all right, alternatively, from the Lyapunov theory, all right, you could see that equivalent results are obtained. All right, equivalent results are obtained, except that, okay, what was important last week, all right, because if I just show you these things, all right, I wanted to go to the stage whereby we see all of these things, all right, for ourselves, all right, without trying to hide behind some big result. All right, so you see, step by step, we derive everything, all right, and we carefully even look at signals and systems, all right, and noting this, even though you could hide behind a result called Babalat's lemma, but we looked at everything carefully and we showed that we got this kind of result. All right, so similarly, if you had looked at the Lyapunov theory, clearly you see down here, this satisfies the Lyapunov theory. Okay, with that, I'm now ready to go on to look at a more significant problem of adaptive control of a class of systems where state variables are measurable. Okay, actually this particular part will be the thing that will be used for your CA3. All right, last time for the motor control experiment, but now I converted everything to simulation, but it's actually based on this. All right, okay, but before I go on to that, and I'll finish this tonight, let me at this point just pause here, check. Anyone has any comments or any questions at this stage? Of course, you know, I'm not in a hurry to run away, right? If you want, right at the end of tonight's class, we will still have time for you to post your questions. Okay, okay, if that, then let's push on. All right, so now we will look at adaptive control for a class of systems with state variables measurable. All right, so and I will post it in this particular way. All right, and let me say that if you read the various books, all right, a lot of them, they don't make the things very clear for you. They don't have a complete result, and you know, they say a lot of things. All right, adaptive control in the way that we want to do it, completely rigorously, all right, whereby, you know, everything is proven. You have to do it very carefully, and the class of systems for which it will work, you also have to describe it very carefully. So here I will post this class of systems where the state variables are measurable, but I will also post that it has a specific structure. All right, and this specific structure you will see is not at all a constraint, because you will see the actual real life systems, many of them actually fall in this class. All right, a very simple example, all right, the motor control. Motor is very real. All right, if you have done the motor control, it will fall within this class of systems. All right, so here further, even though I don't solve the robotic manipulator problem, let me also say that, okay, the robotic manipulator problem for adaptive control can be rearranged into this particular structure, and that's why this particular structure is of great interest. All right, and you will see that, you know, for manipulator control of robotic systems, robotic arm, all right, you can rearrange it into this, and you can also specifically and carefully do adaptive control for it. All right, with that, let's start. So the first thing that I do is I will say that, okay, I'm looking at adaptive control, and now I will look at the situation where the system is written in this particular way, and all the state variables are measurable. Okay, so this is the part that we will do. Okay, but those of you familiar from linear time invariant systems, you know that always doing the control with full state variables measurable is always the first part. Then later on, we have to go on to the second part where state variables are not measurable. and we still want to do the control, all right, you will see in adaptive control, we will also do things in that way. All right, though I want you to, even at this point, even though I say it, I want you to think carefully. In linear time invariant systems, okay, when you have all state variables measurable, okay, you do it. Basically, it boils down to using the concept of state feedback. So that's fine. Then when it comes to the part where you say, look, you don't have all the state variables measurable for linear time invariant system, right? Linear time invariant, let's say EE5101 and so on. So linear time invariant systems, after you cannot measure all the state variables, you can still do your control because you would construct an observer. And we will still do that in adaptive control. Except that even at this point, even though we wouldn't do it yet until another 2 weeks, all right, I want you to just think, all right, here it will not be possible to so easily construct an observer. Why? Because constructing an observer needs knowledge of the system. You go and check up your 5101 or even, any linear systems module. And here we don't know the system, so how do you construct an observer? Okay, this is where you wait 2 more classes and you will see. In adaptive control, we can still do it. All right, okay. Well, that one we wait till that time. All right, so here what we say is that, okay, you give me a system written in state variable form. Okay, it's written in state variable form. All right, state variable, and all the state variable signals are measurable. Okay, all the state variable signals are measurable. There's a system matrix down there. All right, and then of course the input signal is given by you, so of course you have it. All right, then I will pull up a scalar. This is a scalar gain associated with the state vector, the input vector in the state variable description. All right, I pull up a scalar g. All right, it will turn out that I don't need to know the value of g. All right, but again, I will, in this simple method, I need to know the sign of g. All right, just as I needed to know the sign of kp previously. So I pull up the g. All right, then the input vector b, all right, has a structure. Okay, b is an n by 1 vector, all right, and b is known. Okay, as I said, this is how we pose the problem. But as I said, it is not restricted because many classes of real systems, including your robot manipulator arm, when you rearrange it, will actually now you'll be able to now fit it in this class of system. So I'm going to look at control of this class of system. All right, all the state variables are measurable. I got my input. All right, I pull up a G. So just as before, all right, we want, okay, so this is now the system given to me to control. Okay, and then I have some kind of closed loop performance that I want to get, which again, I will now specify by means of a reference model. All right, so quite similar to my first order system, except this is now a system in state variable form. Okay, so now, okay, in this state variable form, here I will follow closely. All right, here I will follow close. So this is essentially now my reference system, right? My reference system, quite important. So let me remember that. Okay, my reference system. Okay, now this is a system in state variable form. So in some ways, it is good that we did the first order system very carefully because we're going to do things quite similar in parallel with it. So you give me a system in state variable form, right? And then you told me all state variables are measurable. Right? If all state variables are measurable, then clearly from what we have done before, all right, we will do state feedback now. We do state feedback, right? Because all my state variables are measurable. So I put my set of state variables down here, the state vector, and then I do state feedback gain. All right. I mean, I'll call this theta x transpose, and these are my state feedback gains. All right. Then, I have a reference sigma. I put a scaling gain. All right. Even my undergraduate state variable control class knows how to do that. All right. Basically, state feedback plus scaling gain. All right, state feedback plus scaling gain, and then just as before, okay, I said, look, if I do this, and I substitute back into the system, right? This will be now just substitute the state feedback gain plus the scaling gain, all right, times R, okay? And clearly now, all right, if you again note that, all right, in your 5101 or even in your first module on linear state variable system, if your state variables are measurable and you know the system, you know you can calculate a perfect control gain and another perfect scaling gain to exactly get you what you want, right? So using the same idea as before, I said, okay. Then what I'll do is that I'll say that, look, you know, there is indeed such a thing as the perfect gain. And I said, look, okay, let's now break my control gain into two parts, all right? Because if I make it exactly, okay, if I make it exactly the perfect gain, right, I make it exactly the perfect gain, then here I would have AP, all right, XP, which is originally from the system, plus G, B, phi X transpose, that's state feedback gain part, and this is a scaling gain part, G theta R, all right? So basically then, what happens then is that when I put in the perfect gain, all right, essentially the perfect gain will be such that this will now be that gain that will exactly make this exactly equal to the closed loop that I want, which would be AM, right? Which would be AM, which was what I said I wanted, right? Which is what I said I wanted, this AM. Okay, so the perfect gain, theta star would give me this. And then also at the same time, that perfect gain, theta R star, all right, would now exactly give me the other part of the scaling gain equals to GM exactly as before, right? Exactly as before, GM. All right, so this will be the perfect gains in parallel with what we had done in the first order case. Okay, then we said, oh, you know, in 5101, right? In 5101, in your undergraduate control, you know how to exactly calculate the perfect gains because you know the system. But now we don't know the system, all right? This is exactly why we're doing adaptive control. So we don't know the system, but we still want to get the same kind of result. So exactly as before, we say, okay, since we know the structure works, right? Since we know the structure works, we will exactly follow the same structure. It is still state feedback, all right? It's still state feedback, except now my state feedback gain, I make it time varying. All right, it is still scaling gain, except my scaling gain, I make it time varying. And this will now be my control law that I'm going to use. And the gains are time varying, so I now have to again be very clear about how I will be designing the adaptation law such that I adapt these time varying gains. All right, and here you can see now, because we've done the first order case, that actually the parallel is there. All right, except that now it scales up to become state variable, state vector matrix form. So this will now essentially simply scale up to be, whereas before it was minus signum KP, now it'll be minus signum G. All right, I still don't need to know the number G, I just need to know the sign. All right, then instead of the scalar gamma 1 positive number, because now I have a whole set of vectors, I now put in a matrix gamma, and the only thing that is needed for this matrix is that this matrix should be symmetric, positive, definite. All right, so not just positive, it has to be a positive, definite matrix. Okay, you go back now. Okay, for those of you who cannot remember, you better go back and check your matrices. All right, what a symmetric, positive, definite matrix is. Okay, so I have that. Then remember previously I have E1, but now it's no longer E1. I have the whole state error now, because remember I can measure my full set of state variable signals, my state vector XP, I can measure it. All right, then I'm generating a reference state variable system that I want the closed loop to look like. So I also have the reference system state variables. So I have the state error now, XP minus XM. All right, so whereas previously I was using the output tracking error E1, now I will use the entire state error XP minus XM, and that will be state error vector. I take E transpose. Then I will need a matrix P, which I'll mention later on in a moment. All right, then I will use the vector B, which is in the way that I post the state variable system. B is the input vector, which is known. And finally, I will use my state vector, measurable state vector X. And that will be how I will adapt. All right, that will be how I will adapt my state variable, state feedback gains, which are time varying. All right, then there's a scaling gain. All right, again, minus signum G. Okay, this is just a scalar. So I put a scalar gamma as before. All right, I still need E transpose PB. All right, and then here, the scaling gain is associated with the reference signal. So I use the reference signal. Okay. So this now will be my adaptive law. All right, this now will be my adaptive law. And as I said, the state tracking error is this. And the gamma matrix, all right, which is now a generalization from the gamma 1 positive number as before, is any n by n positive definite matrix. All right, so I have that. Okay, and then of course, small gamma is any scalar number greater than 0. Okay, then I also use matrix P down here. Okay, the matrix P I will be using, all right, and I will use this from Lyapunov theory, okay, because recall when we earlier talked about Lyapunov theory, and we said we will use it, all right, we said, look, you know, if you say you have a stable system, all right, then all these things are true, but if indeed this is a stable system, this stable system A, I will always be able to write out this particular, all right, yeah, so-called, actually it's a so-called, almost a static Ricardian equation, but also called the Lyapunov equation sometimes. All right, basically, if you have the stable matrix A, all right, from the system, then you will always be able to write A transpose P plus PA equals to minus Q, where you take Q to be any stable positive definite matrix. You pick any matrix Q. You pick any matrix Q, which is stable positive definite. You put your stable A here, you put your stable A transpose here, you put P down here. You will always be able to solve this equation for the P, and the P that comes out will be itself symmetric positive definite. And this is the P that I'm using. All right, this is the P that I'm using. Okay, so because in my reference model is a stable matrix AM, so I use it from there. All right, the P that I'm using above will be from AM transpose P plus P AM equals to minus Q. All right, where Q is chosen by me, all right, and it's any symmetric positive definite matrix. All right, it's any symmetric positive definite matrix. So here, basically, AM is from the closed loop that I want. So I know AM because I'm the one that choose AM. All right, so you have chosen AM. Then you choose any Q, all right, which is symmetric positive definite. Then because this equation is guaranteed to be always solvable for the P, and the P itself, right, always exists, and the P itself is always symmetric positive definite, you take the P and you put it in there in your this design of your adaptive law. Okay, you put this in there in the design of the adaptive law. Okay, how does this work? How does this work? Okay, so now in some ways, actually paralleling now what we have done, all right, in the first order case. All right, so here, okay, let's put back there. because xp dot is equal to apxp plus gbu, and u is just the control law. So remember, control law was just the state feedback gain. All right, we made it time varying. All right, times the state vector. Okay, right. Then the scaling gain, we also made that time varying. All right, then times the reference signal. Right. Then remember that we already said, look, if you put in the perfect gain, you will exactly get AM. All right, so we separated this out as before, the perfect gain plus the error in this particular control gain. And here again, the perfect gain and the error in the control gain, right? So with that, then, okay, you can see that, okay, you can now rewrite. You can now rewrite, because with the rewriting now, this basically just becomes AP plus GB theta X star transpose. All right, and this was G theta R transpose. All right, and then the remaining terms down there, after you rearrange it down there, all right, this will simply be the parameter error in the state feedback gain. All right, the time varying state feedback gain, the parameter error phi, all right, times your state vector. All right, then the parameter error in your scaling gain, phi sub r, all right, times r of t. Okay, so this one is just basically taking this thing and rearranging and then simplifying it, and it will look like that. Okay, with that, then, because we've done, that's why we took so much time to do the first order very carefully. All right, once we do that, then, okay, let's now go and check all the various error signals. Clearly, the first error signal that we're interested in is the state tracking error, which is xp minus xm. Okay, xp minus xm, right? And then, as you recall, we will be interested in is time derivative. Okay, so let's try our time derivative. Okay, this part, I will just say that, look, you just have to do some algebraic manipulations. I leave it to you tonight to double check. And after you do the algebraic manipulations, all right, based on the fact that I have decomposed it like that, all right, because it's AM now, and it's GM now, all right. I decompose it like that, all right. Then if you now rearrange and simplify, all right, you will find that this now can be rewritten as AME plus GB phi X transpose XP, all right, times phi R times R, okay? Okay, and that will be the first set of error signal dynamics that's important. And this would be the equivalent, all right, this would be the equivalent to, in the first order case, all right, to E1 dot. All right, you can even actually, if you look at it carefully, you can even see, all right, that parallel similarity. Okay, so this is the first thing that we need to do: get the error tracking signal. All right, remember this is now a state tracking error. State tracking error. All right, state tracking error. Okay, it looks like that. Okay, then also the same. All right, we want to look at phi dot. And the equivalent of C dot, which is just now phi sub R. All right, and then as before, all right, because phi sub X is just theta sub X of T minus theta X star, and theta star is just a constant as before, right? As before, so now you know that theta phi X will be exactly just equals to theta X dot of T. Right, which was the design law for the adaptive controller. And similarly, all right, phi sub R dot will be just equals to theta sub R dot, because KT minus theta sub R minus theta sub R star. Theta sub R star is a constant, So it's just theta sub r, which remains. So theta sub r dot will be the design part that remains. All right, so remember what these are? All right, this was now minus sigma G capital gamma, all right, E transpose PB times XP. And this was minus sigma G, all right, small gamma, just a scalar positive number, E transpose PB times R. All right, so that was just from our adaptive law. All right, in order to simplify my writing, I'm just going to collect these two things together. I'm going to collect these two things together and make this larger. All right, so if you had n state variables, you would have needed n state feedback gain. So this would be of dimension n. Okay, then this is a scaling gain. This would be 1. So this would be n plus 1. So n plus 1, but I just collect them together. All right, then if I collect them together, then clearly I have the tracking error. All right, my state variable, my state vector is of dimension n. So basically this is of dimension n. All right, this is of dimension n. This is the state feedback signal is of dimension n. This is scaling gain, so just 1. So this n plus 1. Okay, then clearly to consider my so-called ellipsoid function or whatever, it would be quite similar to before. All right, I will be interested now clearly in 1/2 of E1 squared previously, so it will be just E transpose E. All right, then plus previously was 1/2 of phi squared plus c squared. All right, now clearly I will need basically this whole parameter error vector. Okay, so it will turn out to be the n plus 1 dimension phi transpose phi. All right, so you can see over that, but again, I would have to shape it into an ellipsoid. So the shaping part for the E turns out to involve the P matrix, which we calculated before, the symmetric positive definite matrix. All right, calculated out of the so-called stable AM matrix. All right, so this is the same P matrix. All right, from the static Lyapunov equation, P. All right, so you take this P. All right, and remember this P you have to calculate. All right, when you do your CA3, you have to actually calculate it out because you are using it in your adaptation design. All right, you're using this in your adaptation design. So now what happens is that, all right, with that, I'm interested in putting together a quadratic form. So my quadratic form in the first part involves the P. All right, in the second part, I will need, just as before, I had magnitude of Kp. So here I need magnitude of G. All right, then as before, I need 1 over gamma 1, 1 over gamma 2. Now it will turn out to be the gamma matrix inverse. All right, where because I've collected together everything together in this large one, my gamma inverse, all right, my gamma inverse, I've also collected it together as the n by 1 by n by 1 matrix. All right, because what I've done is I've collected the gamma first of all, and the scalar gamma, right? The off diagonal terms is 0. So this is gamma bar, and I need this gamma bar inverse. Okay, here now, all right, with this particular way of writing my V, okay, if you now want to go and double check back on the direct method of Lyapunov, you can go and double check. Go and double check. This is basically a quadratic form with a symmetric positive definite matrix. This is again a quadratic form. If this is symmetric positive definite and this is positive, then gamma inverse is also symmetric positive definite. So you can go and double check. All right. In the same way, this is also positive definite. This is also decrescence. This is also radially unbounded. So I satisfy all the Lyapunov properties if you want to double check. All right. Then here now, the next thing that we would have to do as before is to say, okay, this gives me my ellipsoid function. I'm interested in how this ellipsoid function behaves with time, which means I'm interested in V dot. All right, I'm interested in V dot. Okay. The only complication here is that this has now become a series of messy matrices, but apart from that, conceptually it's not different. All right, so let me write it down. So when I differentiate that, that just becomes 1/2. All right, when I differentiate the first one, it just becomes 2E transpose P E dot. All right, then plus the second part, the 1/2 is also there. All right, then it's just 2 magnitude of G phi transpose gamma bar inverse phi dot. All right, so it just turns out to be like this. Okay, and then what I'll do is I will now next carefully again check out all these terms in here. Okay, I'll do it one by one. I will first of all just check this first part first. I leave this part alone. All right, I leave this part alone, but I will come back to it. I will come back to it. Don't worry, I leave this part alone. All right, I leave this part alone, but I'll come back to it. Okay, so I check the first part first. All right, I check the first part first. Okay, the first part, E dot you saw from before. Okay, the second part is still there. All right, but which I'll come back to it. I just leave it down here. E dot you already saw from above, right? There's an E dot because clearly half and half disappear. You can pull the E transpose out. You can pull the P out. E dot we already have because we just worked that out. All right, we just worked that out. E dot is this, so we put this in there. All right, we put this in there. This will now be equals to AM E. Okay, then plus, all right, G B. Oops, sorry. GB, all right, phi transpose, and even the X, I collect it together, all right, because I've taken the phi to be phi theta and phi sub R. All right, so this one I also collect it to be an n+1 signal, all right, because when I collect it together, this one I can simply put the n state variables xp, I put the R, so this also becomes n+1. So remember this was n+1, and this is now n+1 also, so this is all there. Okay, so it looks like that. And at this point, we will use an interesting, simple result from matrices, all right, which you should have encountered before, okay, but still it's quite something quite clever, all right, something quite clever. I don't really know who was the first person that ever thought of this, but it's quite clever. So we need this intermediate result, and this intermediate result simply says this. Okay, you give me any matrix M, you give me any matrix M, all right, and I will always be able to, write it in this way, all right. I will put M as 1/2 of M here, and then I put plus another 1/2 of M here. All right, I mean, that's obvious, right? 1/2 of M plus 1/2 of M is M. Okay, but this cleverer than that. Then he says, I will add M transpose here. All right. And then if I add M transpose here, because M transpose, you know, is giving me additional terms, I must take it away. All right. And this is a perfectly good way of writing the matrix M. Except that this particular way of decomposing it is very, very clever. Because now when you decompose it this way, this first part of it is always symmetric. Okay, remember what a symmetric matrix is? A symmetric matrix is if you take this matrix, you take its transpose, is exactly the same. And it's correct. It's correct. All right. And then this second part is there. And this second part is what is called anti-symmetric. But what is more important of this anti-symmetric property is that now for this matrix, okay, and this is true for any matrix, it's true for any matrix. All right, if you now take the quadratic form, all right, so you take any vector, say a vector, let's say this is an m by n matrix, n by n matrix, n by n matrix, all right, and then you take a vector q, let's say, a vector q of dimension n. So n by n matrix, you take q transpose mq, all right, and you find that when you take the quadratic form, what happens is that when you take a quadratic form, only this symmetric part remains, because when you take q transpose mq minus q transpose m transpose q, all right, a quadratic form is a scalar. Q transpose mq and q transpose m transpose q turns out to be exactly the same, and they knock each other out. So when you take the quadratic form of this decomposition, all right, only the quadratic form pertaining to this symmetric part remains. And that's very, very important, because we are going to use this. All right, we're going to use this. But basically, this decomposition, all right, is to say this is symmetric, right, and that's anti-symmetric, right? But as I said, the most important part of this anti-symmetric part is that the quadratic form disappears in here, and only this part remains. All right, what that means now is that, look, you know, when I go back and look at the term which I have on V dot, it turns out to be like this. All right. Okay, all these things down here from above, I will let it remain. This part, I will still let it remain. But I want to look at this part, which is a quadratic form. All right, E transpose something E. And this part down here is a matrix, which, you know, unless I decompose it suitably, I cannot handle. Okay, but this decomposition now helps me. All right, this decomposition now helps me, because with this decomposition, all right, with this decomposition, as I said, you know, with the decomposition, what happens now is that when you have the decomposition, anytime you take a quadratic form, what happens is that you can go and double check. This only the symmetric part remains, right? Only the symmetric part remains, right? So noting this, all right, what I'm going to do now is that I have this particular quadratic form. All right, and I'm going to do exactly that. I'm going to now exactly decompose it. All right, because now with that, then what happens is I'm going to take that. All right, it's going to be E transpose. All right, and then I'm going to keep, this is a quadratic form. I only need to keep the symmetric part. I only need to keep the symmetric part. I don't even need to try to write out the anti-symmetric part. So I only keep the symmetric part, which would be P AM plus, okay, then I take its transpose, which will be now turn out to be AM transpose P, but P, okay, maybe let me write it out in full. Right. All right, this would be now P AM again, transpose, all right, times E. Okay, but because P, all right, by the stability theorem, is itself symmetric positive definite. All right, all this now simplifies to 1/2 of E transpose P AM plus AM transpose P, because remember P is symmetric, E. All right, and even better than that, all right, even better than that, remember by design, all right, we had chosen the P such that, all right, this came out from the AM matrix of our reference model design choice, and this was calculated from minus Q, and it is still true. And Q was, to begin with, any symmetric positive definite matrix of our choice. All right, so that's very important. So it came up with this, which now leads to the fact that, okay, as I simplify things further, the first part now from above, all right, the first part now from this thing above here, all right, the first part now from this thing above now simply turns out to be, right, minus 1/2, all right, of E transpose QE from above, right, from above. Okay, then I have the other parts, right? Plus E transpose P, which was there, all right, and then the other parts, which is G, which is a scalar, B, which is an n by 1 vector, then phi n plus 1 vector, x bar n plus 1 vector, and then the other part, all right, which I will now bring in from the earlier part, all right, that I had kind of reserved. I'll just bring that down in, and this is now, if you check from above, this is magnitude G, phi transpose gamma bar inverse phi dot. All right, so we have that. All right, and then if you now go carefully check, right? If you go carefully check, you will see that, all right, because all right, what we have now is this particular thing down here, all right? So clearly, this is the x bar that we have, all right? And you can clearly see that, okay, phi dot is this. Okay, you can double check phi dot is this. And if you now, just as before, as in the first order term, check all these things now carefully, all right? Minus signal of G and G, all right? No, sorry, no G here. Minus signum G, right? So here, all right, minus signum G and G, gamma bar and gamma bar inverse knocking each other out, E transpose PB, E transpose PB. All right, this gives itself G, and these things are down there. All right, you will see, if you check this very carefully, you will see that just as before, all right, just as before, because of this, all right, this term cancels out this term exactly. All right, just as before, cancels out this thing. Now leaving us now with, all right, V dot equals to minus 1/2 of E transpose QE. All right, and if we, basically what we do now is follow almost everything previously as before. That now, all right, with the V being ellipsoid surface, all right, and you're starting from some whatever numbers to begin with, but that will be, whatever it is still some particular fixed number. You started off, and then V dot is less than or equals to 0. All right, what that straight away implies for us is, again, we get boundedness. All right, we get boundedness because we are looking at this quadratic form. Right, we're looking at this quadratic form, and we just shown that V dot is less than or equals to 0, which means that this first set of signals, this second set of signals, this third set of signals in here, forming the ellipsoid, these signals are all bounded. All right, because we got V dot less than or equals to 0. So the first result that we get is as before, all right, that we get boundedness of solution, all right, norm of E, norm of phi x, all right, the state feedback signals, the scaling gain, all right, these are bounded for all t greater than or equals to t0 from the starting time. All right, as before. All right, then the rest of it actually follows in the same way, because next thing you will do is you will take this, you will integrate it. All right, and then you can check it is certainly bounded above from a fixed number, which means that norm of E is square integrable. It belongs to the class of capital L2 signals. All right, then you check E dot. Okay, in the same way, you can check that E dot is bounded, which means E dot belongs to the category of L infinity signals. And together, these two results implies as before that we exactly get the performance that we want. All right, we exactly get the performance that we want, that in this design, all right, limit as t tends to infinity of norm of E of t, okay, which is, all right, our state vector, all right, compared with the closed loop reference set of signals that we want it to attain, all right, that this is now indeed converging to 0, which means that now in this adaptive controller that we set up, we have just guaranteed for everyone that again we get perfect tracking. All right, I'm done. But even before I finish off, I want you to note very carefully again, all right, what we have done for the first order, what we've done here. It shows some very, very nice things, but and it says a lot, but there are some things that it is completely silent and doesn't say. All right, so go and think about it. All right, very, very important, particularly for 6104 people, okay? I want you to think deeper. Okay, with that, I'm done. Let me stop the recording.